basic problem solving. We have already solved one question on this, which was based on flattening a binary tree into a linked list. So do check out that question as well if you haven't yet. So today we are going to be looking at the second problem in this, which is going to be the problem statement, where we say that we have been given a binary search tree and you need to check whether the tree is balanced or not. Alright, so in this question, first we'll figure out an optimized way to solve this problem, right? And then we will implement our logic to see if our knowledge was correct or not. Alright, so to actually solve this question, first you should know when do we actually call a tree balanced and in what situations do we actually call the tree not balanced. So first, in theoretical way, we should be clear for an understanding about balancing concept. Okay, so let me help you with a very basic definition. So we basically say that a tree is balanced, or a binary tree rather, is balanced if and only if, first, three conditions over here. That the left subtree is balanced, the right subtree is balanced, right? And for every node, I'll write it over here. Right? Every node differs in the height, okay? By 1, okay? Now let me explain this concept to you by taking a few examples. For example, let's say consider a tree, let's say the root node is 2, 1, 5, 6 and 7. Okay, so for this particular tree, what I will see is, let's say take any particular node. Okay, now what is the height of the left subtree over here? If I consider this as height 0 and this at height 1, I can say that the height of the left subtree is 1. Okay, and the height of the right subtree is basically 0. So when I take the difference of these, 1 minus 0, it comes out to be 1 only. So the difference should never be greater than 1, okay? As long as it's less than or equal to 1, we are good. So here, and that should be true for every node. For this node, the answer is 1. For this node, the answer is 0, because this height is also 0, this height is also 0. So 0 minus 0 is 0, okay? For this also, since this is a leaf node, you don't have to bother about it. And this is. So for every node, that rule is valid. Now let's consider this tree. Yeah. So for this node, the height of the difference is what? Here the height is 2, okay, and here the height is 0. So when you take out the difference is 2, right? And I always said that the difference of the height of the left and the right subtree should never exceed by 1. Okay, for this node also, this is what? 1 on this side, or rather this is 3 we can consider, right? Height of the left subtree can be 2 and the height of the entire subtree is this. Okay, similarly for this node, what is the height of the left subtree? 1. Height of the right subtree is 0. So this is still justified over here, but you can see that for this node it is not justified. So all these three conditions should be there. So here what you will see is that the left subtree was balanced, the right subtree was also balanced, right? But for the root node, there was a node that existed for which this rule did not verify or did not stand hold true. Okay, so this is how we basically do this. For every node, difference, I'll write it down in a better way. Difference in the height of left subtree and right subtree should be only by 1 and not more than that. It could be 0, it could be 1, but it could not be more than that. Okay, and it's like an absolute. So this is also a balanced tree, like here. Alright, so here the height of the left subtree is 0, the height of the right subtree is 1. Okay, so we always take the mod of the difference. This is still 1. Okay, so it's not like we have to consider in the difference left subtree or the right subtree. Any ordering could be preferred in the difference, but the absolute difference, okay, should be 1. So that's what the question is basically expecting you to do over here. So what we're going to do is, you must have already solved the question for finding the height of a binary tree, right? So we can very well use this concept and apply it at each and every level to basically find the height. Okay, and then just recursively solve this question. Always and always remember, if it's a question based on tree, recursion should be first thing that comes to your mind. There can obviously be an iterative way to solve the questions also, but I strongly feel that when you solve questions using recursion, it becomes a lot more easy to implement the approach, and it's a lot more simplistic to understand as well. Okay, so I would highly recommend first to make sure that your understanding for the balancing concept is clear, and then only you move ahead. Okay, just to reiterate on that, a tree is a balanced tree if these three conditions are satisfied. The left subtree is balanced, the right subtree is also balanced, and for every node, the difference in the height of the left subtree and the right subtree should never be greater, or I would say not just difference, absolute difference. Okay, in the height of the left and the right subtree should never be greater than 1. If this is being satisfied, then there you go, your question is complete, and you can say that you have your answer over there. Okay, one more important thing to remember over here, right? If there is just like one node, okay, or if there is no node, okay, you can consider it, let's say this to be a height of 0 and this to be a height of -1, or some people consider this to be a height of -1 and this as nothing. So feel free to use whatever definitions you want. The answer in most scenarios should be same. Also, for solving this question, you should also know the concept of how to find the height in a binary tree. Okay, so I would recommend to just quickly revise on that aspect as well. So if you have been given a tree, how do you find the height of the tree? Okay, so you take the height of the left subtree, you take the height of the right subtree, and then you take the maximum of them. For example, if I have a tree given over here, okay, what I will do is, to find the height of this tree, I will find the height of the left subtree, which is 1. I will find the height of the right subtree, which is 2, right? Take the maximum of it, 1, 2, and then add +1 for this edge. Okay, so this will be 2 + 1 equal to 3, and this is basically the height of the tree equal to 3. So this is also, that is going to come handy while writing the code. So let's take a look at now the implementation. I'll directly write, first I'll write the function height. So we are passing the root, and if the root is null, I'm considering that to be a scenario 0, so I'll return 0 in that case. Okay, otherwise what I will do is, I will take the height of the left subtree, okay, and I will also apply the maximum. I will take it the maximum with the height of the right subtree, and I will do a +1. Good enough? Now we need to check whether a tree is balanced or not. Okay, so here again, if the root is equal to null, you simply return true, because if there's nothing else, then what you do is, you find the height of the left subtree, you find the height of the left subtree, and then you try to put into words what the implementation we thought of. If math.absolute, the difference of the left and the right subtree is less than equal to 1, and the is balanced root dot left subtree is correct, and is balanced is the right subtree as well. Okay, so if all this is indeed true, if all this is indeed true, we return true. If any of these conditions does not work, we will return false. Okay, Since we are taking a tree over here, we'll have to define a node structure as well. Because trees are defined from a node which contains theta and left child and the right child. Alright? Now what I'll do is I will use this tree only over here, and the output for this should be that it is not balanced. So I'll just directly pick up the code for that. Okay, and now I will call the is balanced part. So here I'll pass the root node. If this is indeed true, that means we'll print tree is balanced. Otherwise we will print tree is not balanced. Okay, let's see if this works or not. Tree is not balanced. So if I simply remove this, right, that means I don't have this anymore, then the tree should be balanced. Let's see. See, in that scenario, the tree is balanced. Always remember, for both the things, we are doing three things only. Since it's a recursion question, we are doing the base case. Okay. Here we have the recursive call for the left and the right subtree, and the self work also happening, which is doing +1 to the max. That is a self work. Here also you can see that we have a base case. Here we are having the recursive call. Okay, and here we are doing some self work, which is like checking the condition. So don't bother yourself a lot how internally things are working. Just bother yourself with the fact that how you are going to implement the logic in terms of recursion. Once you have that thing figured out, trust me, there is nothing else that needs to be done for this particular code. Everything is written and everything is provided in a plain simple sense. Alright, so I hope I was helpful in helping you understand this particular question. Right, please go ahead and implement this one on your own as well to get a better understanding of how the code is working. Thank you, and I will see you in the next question.